This tutorial will show you what a seal-in circuit is. It is just a latching relay, and although there are ways to latch a relay mechanically, there's different designs for that. What we're talking about is electrically latching it. So what happens is you pull a little trick where the relay, when it's activated, uses a set of its own contacts to connect power to itself and stay on even after the button that was pressed to turn it on is released. So let's draw that, and I want to do it schematically, but at the same time we'll show you what the ladder diagram would look like, and that'll serve as an introduction to ladder diagrams. So schematically, we have a voltage source of 24 volts, and we would write it like this. In a ladder diagram, it's just going to be rails running down the side. So it's going to be a 24 volt rail and a 0 volt rail here. Okay. Now, we need a relay coil. So the coil of our relay, well, schematically, we would draw it like this. In a ladder diagram, it would just maybe be over here on the right side, just a little C for coil, and we will connect it already to the 0 volt side, so we can do that. Okay. And maybe we'll have a push button and to do the activation, and the push button, let's see, in our schematic we might put it here. And you can actually use that same push button symbol in a ladder diagram, or if you want to, it's of course a normally open contact, which is you could also draw it like this. Okay, so we have a normally open contact. When we press it, the coil of the relay will be activated. Now, it's not going to be latching yet, of course. That just turns the coil on, and when you release it, the relay turns off. So we said what we need is to pull a little trick here. We'll use one of the relay contacts to connect power to itself. So we're going to grab, in our schematic, we're going to do it this way. We're going to grab that 24 volts, bring it over to a set of contacts, and when the relay turns on, it'll take the 24 volts through its own contacts back to itself, back to its own coil. Now when you press that button, the coil turns on, closes the contacts, connects 24 to itself. You can release that button and the relay will maintain its on status. It'll have 24 volts. And you'll see why we like ladder diagrams here. In this case, I might put some labels here. This could be like push button 1 or something, or I could call that the latch, but I would label it. And what I'm going to need is a set of contacts from the relay itself. And if you see, they're actually ORed. It's a little more easy to see it in the ladder diagram. We could just reference these as, this relay. Maybe we have a name for it, but we'll just put that set of contacts. I don't know. The labeling in ladder diagrams, you have to kind of, hopefully they come with a key, or you have to sort of decipher it. I think in our exercises we call it main disconnect, maybe. If we gave it that name, then I could call these contacts, these are a set of normally open contacts controlled by the main disconnect relay. Okay, but in any case, that would be the association. Whatever name you give your relay, you also put that name here to associate these contacts are part of this relay. Can you see they're in parallel? I mean, here you share this point, and they also share this point. So in either drawing, they are parallel action. So now when you press the push button down, these contacts close also because of the powered relay. When you release the push button, these are still closed. Okay. So this will latch the relay. Now we have to think of a way to unlatch it, because here there's really no way to get that relay to turn off. So you put a normally closed, maybe push button there. And we now have our latch and our unlatch, if you want to call it that. Same thing, just squeeze in a set of contacts here. The ladder symbol for ladder diagram symbol for normally closed contacts is just contacts with a line through them. Yeah. Maybe I'll just call these latch and unlatch too, so you can see how they associate. Okay. So there's the ladder representation, and we now have the classic seal-in circuit. It seals in when you hit the latch. It unseals when you hit the unlatch. It is a latching relay. It also gets the name three-wire control. Sometimes an electrician will call it that because it oftentimes is associated with the classic start-stop button. And if you have a start button and a stop button in an enclosure, well, this is going to be your start. This is going to be your stop. And can you see it's going to take 3 wires to come out of that box, right? I mean, here's a wire, here's a wire, here's a wire. So that's why it gets the name, you know, 3-wire control, because from your push button enclosure, you're going to just need 3 wires coming from the start, stop, push buttons. That's why you get the 3-wire control name. Okay. The seal-in circuit, it is very useful. It shows up in different contexts. It is always doing the latching and unlatching, but like in one context, the E-stop button, the panic button that you press, this one here, could be this normally closed contact, and it'll pop off the latched contactor, which would be in the first, the exercise we're going to do, the first one with seal-in circuits, is going to be to put an E-stop and reset in place. It's a safety circuit design. You know, you have your, maybe your reset button and your E-stop. And what happens is if something's going wrong, you just hit the E-stop. This relay pops off, which is really going to kill power to everything. So the whole system, the whole machine goes down. And then the only way to bring it back is to, well, you twist the E-stop, you know, to reset the E-stop, not reset the circuit, but the E-stop will reset. So this will close again. This is still off until you press the reset button, which is the latching button. Then the mains contactor, the big relay that turns everything, that restores power to the cabinet, it'll latch again when you press this. So that feature, it does give you the panic button to hit. It does something else that we should mention. Don't look at the start stop yet. We'll talk about that in a minute. But the E-stop reset, it's sitting there as the panic button, but it also naturally solves a problem if the power would fail. Like, let's say for the plant or for that line or something, I don't know, let's say an electric storm's going through, I don't know. Think of some scenario, you lose power for whatever reason. Even if it's just in a small shop, that might be more realistic, because I know plants have backup power and stuff. But machines need to be designed so that if you lose power and the machine goes down, you don't want the machine jumping back to life when power is restored. And that will happen if you had something simple, like remember when we just had our For this activity, let's say you have the motor running forward, okay? Now you lose power to the machine. Power fails, blinks off or something. So, okay, your machine's down. You go grab a broom to do some cleanup or whatever. You're doing some cleanup on the machine when all of a sudden power is restored. And look, that machine is going to jump back to life. So if it's a big saw blade, for example, that's bad news, right? That's going to surprise people. You know, yes, if you remember when power goes down to go over and reset the thing to off, you could avoid that, but you have to remember to do that. And that's not necessarily a guaranteed thing. So the machine's down, right? And everybody's like, okay, head to break, take a break. Power comes back, the machine jumps to life. That's the scenario we want to avoid. And the good news is the seal-in circuit takes care of that, because yes, it provided a panic button, but it also will unlatch itself on power failure. So when you lose power, a seal-in circuit automatically resets to off. When power comes back, you can see what the scenario is, I think, right? You lose power, the relay goes off, power comes back, the relay is not going to jump back on because you're back to this reset state. What do you have to do? Well, you'll see an amber light telling you that you need to reset. Okay, when you hit the amber light, now power's restored to the machine. Yeah. And so you get a lot of features from this latching relay seal-in circuit that are desirable. And yes, you might, if you're thinking about it, maybe the thought occurred to you that if we were still using this fixed position switch and it was left in forward, it's true the machine went down and it doesn't jump back to life when power is restored, but the operator, when he hits reset, it would jump back to life, which could still catch somebody by surprise. So that's the next exercise, is after we do put an Estop in place, we'll replace this fixed position switch with another seal-in circuit, and that would be sort of like a start-stop circuit. I mean, this is better than this because it's just momentary input, you know, start, stop. And what you want is even the start of a motor, of course, you want that to reset to off too. The bottom line is, if you got a start button or a start switch for a motor, you only want the motor to start from that action. You don't want it to start when somebody just tries to reset the power to the line. You don't want it to start when power from the outside comes back on line, you know, if it was power being restored to the building. All those things can surprise people. So that's a general thing that covers sort of this example. In this case, you're trying to avoid a system starting up and catching somebody by surprise. So yeah, so that just gives you some idea. I mean, we'll be running those exact examples, so don't feel like you have to be perfectly straight on all that. That's what the exercises will do for you. They'll drive that home, and you'll be able to actually try out the scenarios. As you wire them, we'll work our way towards better and better circuits. We'll just keep improving it. You know, we'll say, now we've added this, but look, there's still a problem. And now we've solved that, but we still have this to deal with. So we'll kind of work our way towards good design by showing you the improvements that you make along the way. That's the idea. But this will be a good second exercise for you. Just getting, you know, you'll have your, I think actually we'll reset the motor. You can see on the prints, I'll have the ladder diagrams for you to follow. So you'll use the ladder diagrams to wire up what they show. And I think what we'll do is we'll after we do the forward, off, and reverse with the fixed 3-position switch, we're going to maybe simplify that with just a 2-position that turns a motor on and off. And we'll use that on and off motor control, and we'll add a seal-in, you know, a seal-in circuit with an Estop and a reset. We can have an indicator. I think I have an indicator on the portable trainer that indicates when the Estop's pressed, type thing. But we'll sort of do this kind of a grouping where you just have a motor on or off, but you've added an e-stop, and then we'll replace the on and off with a better on and off, start and stop, which will be a seal-in circuit here and another seal-in circuit to start and stop the motor. And so there's two seal-in circuits, one to start and stop the motor, one as a panic button, and also a mains reset if your power fails in the building and so on. Just to give you sort of the forest for the trees. We'll actually get into the exercises if this didn't make sense. Hopefully, piece by piece, you can make sense of it. And the seal-in circuit, it also pops off in the case of a short circuit. So that'd be just another nice feature about it. If something would happen and a fault occurs, like a short, and you lose your voltage for that reason, it won't stay that way for long. It'll self-protect, and the relay will pop open because there's no voltage to keep it shut. So that's another nice feature. And one last thing, while we're talking about the general mindset of industrial control design, you're always going to use normally closed contacts to stop things. Like the e-stop circuit, it uses the normally closed contact, because it's probably the obvious choice. But it's absolutely important that you would not use a normally open contact to send a signal to stop something. Because the problem there is if a wire was loose or a wire broke or your signal path just did not have integrity, something came disconnected, then when you go to hit the panic button to stop things, that signal won't get through because a wire came off and you didn't know it. You can see you've solved that problem when you use normally closed contacts for your signal to signal everything to stop. Picture this. Picture a wire coming loose and you lost your actual wiring for your safety circuit. What would happen? Well, it's based on being broken open to stop things. So if a wire comes off, things will stop. Or another way you might look at it is things won't be able to start. So the normally closed contacts always are used for that reason. That way, worst case, your actual wiring for your safety circuit is not intact. That's okay. That just means the machine comes to a grinding halt. It stops or it won't start. So you can't start the machine if the safety circuit isn't in place, intact, because it relies on everything to be closed. So that means the wiring is good, if that makes sense. And likewise, you always use normally open contacts to start things because, again, if you use normally closed contacts and a wire came off, then the machine could jump to life. So you don't want to use a normally closed contact to start things where the action you're looking for is to open something in the signal path, and then when it opens, now things start, because again, a wire could come loose or break, and all of a sudden the machine would jump to life. So always normally open, and worst case, a wire's loose or off. So it's open and you can't close it because the wire is not there. Well, that just means you can't start it. Okay. But it doesn't mean it would false start. If a wire falls off in a normally open scheme, it just remains open. So there's no start signal generated, if that makes sense. So just to help you, again, with some real general mindsets that come into play with industrial controls. The bottom line is you're trying to make things sort of fail safe. So failure would be maybe wires coming loose or falling off or breaking. And you want that failure to still be a safe condition. You don't want that failure to result in something turning on, or you don't want that failure to result in something not being able to be turned off. Okay. So just as we wrap up the video, we could maybe review, I guess, the mindsets. You always want to ask yourself, what are your indicators indicating in a very precise way? We look at exactly what they're indicating. It's nice to have positive indication. so that you don't get fooled by a wire just coming off or something. Redundancy is nice. It also helps not get fooled. As long as everything's agreeing, you have a reasonable certainty. And then redundancy for other reasons too. Maybe it will just prevent failure if you have redundancy. And speaking of failure, you would prefer things to fail in a safe manner. So look for those failures and look for how it's going to fail in a safe way. So, okay.